Is it okay? Thank you. Welcome back, everyone. Please take your seats. We are starting our afternoon session in a minute. Let me introduce myself first. Sorry, Marco. My name is Victoria Földvári, and I was a student of András Lipschitz, which makes me a mathematical granddaughter of John Morgan. And why am I mentioning this? Because Josh already mentioned this mass genealogy project. I hope most of you are familiar with that. And I would like to kindly ask you to take a moment to think about that. If given this piece of information, are you my mathematical cousins or further maybe distant relatives? I will let you know in an hour after Marco's talk why this information might be interesting for you when making the group photo after Marco's talk. But why we are gathering here for now is it's my pleasure to introduce our first speaker this afternoon, Marco Golla from the University of Nantes. But am I okay to also say that we are proud to consider you partially local here in Budapest? And he is going to talk about topological non-realizability of line arrangements.
Thank you, Vicky, for the introduction, and thanks everybody for showing up. Indeed, I feel a bit like a local. I was a postdoc here a while back, but I've never been in this room before, and it's quite gorgeous. Anyway, today I'm going to tell you about line arrangements from a very, very topological viewpoint. It's the symplectic day, so the word symplectic will appear here and there throughout the talk, but it will not be the main topic. And most of what I'm talking about could have been done in, I don't know, 1966, so something like 60 years ago, and, well, we'll see how it goes. So, where are we? We're thinking about objects in the complex projective plane, CP2. This is a complex surface, projective. And from the topological perspective, this is a closed-oriented smooth form manifold. And as a complex surface, we can look at its complex submanifolds, so it contains curves that are one-dimensional complex objects, which are defined by equations, which in the case of CP2, they're just homogeneous equations in 3 variables, which will usually be x, y, and z in the talk. So the first example, the simplest example, is degree 1 curves, so curves defined by linear polynomials, and these are called complex lines. And each of them is isomorphic to CP1 in the complex category, and in the smooth category, these are just Riemann spheres, so they're diffeomorphic to S2. And a line arrangement is just a collection of lines. So it's a curve that is defined by a product of linear factors. And we ask that this product is square-free. So we don't want double lines, we don't want multiplicities of lines, we don't want to think like algebraic geometers, we're topologists. So what's one characterizing property of lines in CP2? Well, every 2 of them meet exactly once, positively and transversely. As complex objects, they are naturally oriented, so it makes sense to think about signs of intersections. And there's an underlying combinatorial structure that I'm not going to talk a lot about, which is the set of incidence relations. You want to know, given a set of lines, who intersects whom. And the underlying combinatorial object, well, you can think about it as a set of pairs, points and lines, where the line belongs to, the point belongs to the line. And this is called by some people a rank 3 matroid, possibly with some adjective that I'm ignoring and that I don't actually know about. Or during the talk, it will most likely be called just a combinatorial line arrangement. So we're interested in realizations or non-realizability of line arrangements. So we say that a combinatorial line arrangement is realized if there exists a line arrangement in CP2. So a combinatorial object is realized by something geometric if there exist lines defined by equations that realize these incidence relations. But we're topologists, and we like to make things a bit wigglier and a bit softer, so we can soften this notion of realizability, and we can talk about, well, symplectic realizability or symplectic realizations, where we ask that our lines are not realized by actual 0 sets of linear equations, but by pseudo-holomorphic spheres. So by J-holomorphic lines for some almost complex structure J compatible with the symplectic structure on CP2. We can make them smooth. Every symplectic line is in particular a smoothly embedded two-sphere, and we can ask, well, let's soften things a bit further, and let's not demand that things are pseudo-holomorphic. Let's just demand that they are smoothly embedded and in the right homology class and intersecting transversely pairwise once. Or we can even go wilder and think about the locally flat category. So we can think about locally flat realizations of line arrangements where we ask that each sphere is locally flatly embedded, so that locally and therefore globally there's a tubular neighborhood. And well, one might ask, well, is this even meaningful? Is there more? Is not everything really complex? And the answer is no. There are simple enough examples of line arrangements, and we've actually seen one this morning in Laura's talk that are not realized algebra geometrically, but they are realized symplectically. And it's kind of easy to construct one. So we start with 2 lines and 3 pairs of points on these marked lines. They are colored, so they come in pairs. And we join pairs of points with different colors. So I don't know if you saw, but the 2 red lines pass through the pairs of non-red points, the 2 green lines through the 2 non-green points, and so on. And Pappus's theorem tells us that given this configuration, there's a line that passes through the 3 intersection points in the middle. Now, topologically, we can start with the same configuration and just bump it up a bit to remove one of the triple intersections that are provided by Pappus's theorem. This is clearly something that is smoothly embedded and has the same pairwise transverse intersections properties. But actually what happens is that this is realized symplectically. We will see that a bit later. This perturbation can be done symplectically. And this configuration is called the pseudo-Pappus configuration. And it's the first and maybe the simplest example of something that is realized symplectically but not holomorphically. Just a bit of terminology and notation for stating results and just to have some common ground. We will call the degree of a line arrangement the number of lines. If we think algebra geometrically, this is the degree of the defining polynomial. And given a point in the line arrangement, we call MP its multiplicity. That's the number of lines this is incident to. Algebra geometrically, this is the multiplicity of the singularity of the arrangement at that point. And given a line arrangement, we call Tm, for an integer m, we call Tm the number of points of multiplicity m. Don't ask me to do the computation, but I think that the Pappus arrangement has something like 9 points of multiplicity 3. So Tm is 9, I think. And the rest is double points, and the number can be computed combinatorially. Good. Let's state the main results. So a few years back, I proved this theorem, and I will tell you later why to me this is relevant and why I care about it. So if a locally flat line arrangement of CP2 has only triple points, so this condition Tm is 0 if m is not 3, means that all singular points of the line arrangement have multiplicity 3, so they're all triple points, then its degree can only be 1 or 3 modulo 8. Let me leave it at that, and later I will motivate it a bit more, and we'll give you some examples. The second theorem, in collaboration with Paolo Aceto, if we have a smooth line arrangement in CP2, and this one is smooth and the first one is locally flat, such that all multiplicities are odd, this is just a rephrasing of the assumption, and the arrangement is not the silly line arrangement where all lines pass through a point, then we have an inequality that tells us that, in essence, we cannot have too many points of high multiplicity, or if we want to think about it in different ways, it tells us that any smoothly realized line arrangement with only odd multiplicity has to have some point of low multiplicity. And the third theorem, also in collaboration with Paolo Aceto, if A is a locally flat now line arrangement in CP2 with even degree and with all multiplicities even, so it's in a sense the opposite of the previous one, then we have kind of surprisingly a very similar inequality on the number of points of a given multiplicity, which, I mean, this is kind of hard to read. It's hard to read what this means in practice, but as a corollary, this means that every locally flatly realized line arrangement in CP2 has to have some point of multiplicity, either 2 or 4. And let me mention something about these results. These results use something which is a lot weaker than the whole set of incidence relations. If you think about it for a bit, telling you how many points you have in a line arrangement that have a given multiplicity is kind of a very small amount of information on the line arrangement. It doesn't tell you too much about which lines intersect which. And in particular, if you're given a sequence of TMs, there can be multiple lifts, multiple different combinatorial realizations. And in fact, this number in general explodes. So for instance, if you look at line arrangements with triple points, this number is relatively small up to degree maybe 13, but I think that already in degree 19, you have something like 11 billion possible different combinatorial realizations, only with triple points. So let me give you some background in history and maybe tell you a bit about why I care about this problem. The basic question is, given something combinatorial, when can we realize it, and in which category can we realize it? So stated a bit more formally, which matroids or which combinatorial line arrangements actually do come from line arrangements, let's say, over R or over C. And one of the most ancient instances of this problem is the so-called orchard problem. You are a farmer, you want to plant trees in your orchard, and you want to plant them nicely so that whenever you have 2 trees, there's a third one somewhere else that is aligned with the first 2 that you planted. And you can plant only finitely many trees because you're a farmer, you know. And there's a silly solution. You just plant them all in one line, and that's kind of the silly solution. So you want to prevent that. You want to say, is there anything else? So can we? You go up the stairs at Régnier, and you look at the portraits that are up the stairs at Régnier, and you find this person. This person is Tibor Galai. And Tibor Galai tells you, no. So this was actually known also as the Sylvester Galai problem. And there's a refinement of this problem. So this is a yes-no question, but there's a quantitative version of this problem that you can ask. And there's an inequality behind it that was proved by Melchior, I think in the 50s, that tells you that if a line arrangement in RP2 is realized by real lines, and it's not a pencil, which means that it's not this line arrangement where all the lines go through one point, then the number of double points cannot be 0. You have to have at least 3 double points. And you can make it quantitatively more precise. And actually, the proof is really, really cool. It's a topological proof. If you get bored, at some point you can ask me for a hint, but you can start thinking about it on your own. And who's the chair? Is Vicky. And Vicky will come and chase you if you want to ask me for a hint. And the cool thing is that this is a topological proof, so it works for things that are a lot wobblier and a lot softer than real line arrangements. So let's spend maybe one slide thinking about real stuff. So there's some terminology that Laura already used this morning, that of pseudo-line arrangements. A topological realization of a line arrangement by real lines in the real projective plane is called a pseudo-line arrangement. And the underlying combinatorics has a bit more structure than the combinatorics of complex line arrangements or abstract line arrangements, because points on a real projective line have a cyclic ordering. And there's a way of encoding this cyclic ordering within the matroid, you have to add some extra structure, and this extra structure gives you what's called an oriented matroid. And kind of surprisingly to me, people can actually prove that a matroid is realized by a real pseudo-line arrangement if and only if it can be given an orientation. And let me also mention one result due to Laura and Danny, who already gave talks at this conference. If you have a real pseudo-line arrangement, you can make it symplectic. So it comes from a symplectic line arrangement with a conjugation-like symmetry, so an orientation-preserving involution of CP2 that preserves the lines setwise and that fixes an RP2 embedded in CP2. And the intersection of this symplectic line arrangement with this fixed point set is a pseudo-line arrangement that you want to consider. So for instance, if you take the pseudo-Pappus arrangement that we were talking about earlier, this is a real line arrangement, and indeed it does come from a symplectic line arrangement that you can construct, or that they could construct. And by the way, let me advertise this paper. This is one of my favorite papers. I learned a lot from it, and it's really, really cool. And there are lots of cool results. More will be mentioned later. So let's get back to the complex world, and actually not really, but so let me give some more examples of line arrangements, of combinatorial line arrangements. If you take the set of all lines in a projective plane over a finite field, this is a line arrangement of degree q squared plus q plus 1, if you look at the projective plane over the field with q elements. And all its singular points, there are as many points as there are lines, and all the points have the same multiplicity, which is q plus 1. And all the lines contain q plus 1 points. There's a symmetry there. Another example, which is, I think, a very cool example, is this line arrangement that we'll also meet later. This is defined by 3 cubic polynomials. It doesn't look a lot like a line arrangement, but actually each of these polynomials factors into linear factors. And it's the union of 9 lines in CP2. And if you compute the pairwise intersection, you actually realize that through whenever 2 lines meet, there's a third one that goes through the same point. So this is an example of a line arrangement which is defined over C that has 12 points of multiplicity 3 and no points of multiplicity 2. So this is interesting because on the one hand it tells you that this cannot be realized by real pseudo-lines or real lines. So it's something actually a genuinely complex phenomenon. And on the other, it tells you that the Melchior's inequality cannot hold in the complex setup. Nevertheless, there is a Melchior-type inequality that one can prove, and this is due to Hirzebruch. Hirzebruch proved that if A is a non-trivial line arrangement, and now non-trivial means it's not the silly one that I told you earlier, but also a less silly one when you take all lines through a point and then an extra generic line, then this new inequality holds, which in particular tells you that in any complex line arrangement, maybe you don't have double points, but if you don't have double points, you have to have triple points. And in general, you have at least one of the two. And let me mention that actually this inequality can be improved if you use more sophisticated techniques. There's a result due to Pokora when you can improve something on the right-hand side. And as a corollary, as I said, you cannot have, you need to have triple or double points, so you cannot realize projective planes over finite fields because they have very large multiplicities at all points. So let me mention 2 things about the proof. It has 2 main ingredients. One is abelian covers, non-cyclic, but abelian covers of CP2. And the other one is the Bogomolov-Miyaoka-Yau inequality, which holds for complex surfaces, minimal complex surfaces of general type, and it's not C1 squared less than C2. There's a 3 missing, so it's C1 squared less than 3 C2. And while the first ingredient is very much topological, one can just use this part of the argument one can use exactly in the same way topologically. The second part is definitely not topological. There's no topological BMY inequality. But maybe it's symplectic. We don't know yet. This is one of the open questions that people care about a lot in symplectic four-dimensional topology. Nevertheless, we don't have this inequality, but one can still prove something about certain line arrangements with high multiplicities. And in the same paper that I mentioned earlier by Danny and Laura, they proved that no projective plane over a finite field can be topologically realized in CP2, actually by locally flatly embedded surfaces. So it's a locally flat proof. So motivating questions, as I really like Hirzebruch's inequality. I like the proof. I think it's very cool. It's relatively simple. It uses some hard technology, but it's fairly simple after all. And the question is, can we make the proof even, I don't know if simpler, but can we make it softer? Can we make it topological? Can we make it symplectic? Oops. And the second question that I really like, and that I spent way too much time thinking about, is whether there exist line arrangements with only triple points. And we have two examples. One of them is a silly example of 3 lines all going through the same point. Well, great. And the other example is the dual Hesse arrangement. That's the example that we saw earlier, where we had degree 9 and 12 triple points. And it's completely open whether there are more than these line arrangements in general. And I think that the result that I was mentioning earlier, it's the first result that excludes infinitely many degrees that is not combinatorial. If you change a bit your setup, so if you start working in positive characteristics, then yes, there are other examples where the Fano plane, so the projective plane over F2 is one example, and it is realized in characteristic 2. But there are other examples in characteristic 2 due to Kühne, Schemberg, and Tutaj-Kaszinska, and examples in odd characteristic due to Xavier Rouleau. So there's something that one can do geometrically in positive characteristics. In characteristic 0, we don't know that much. And the other problem that I like things that are sort of symmetric in a way, and configurations are a classical example of line arrangements that people like a lot. So the question is, for which n and k is there an nk configuration that is realized symplectically or topologically or locally flatly, whichever you choose. What is a configuration? So an nk configuration is a combinatorial line arrangement of degree n, so n is the number of lines, such that you can find n points in your arrangement, such that each line contains k of these points, and through each of these points there are k lines going through it. It's a lot to process, so just these are things that are very symmetric. One silly example is when k is equal to 2. For any n, you have the n-gon, which is such an example. You just take the n points of an n-gon, and you take the sides of the n-gon. This is an n2 configuration. And projective planes over finite fields, these are sort of an extremal example. They're example where there's a configuration where n is q squared plus q plus 1, and k is equal to q plus 1. You have q squared plus q plus 1 points and lines. Each line contains q plus 1 points, and through each point you have q plus 1 lines. So I want to maybe pause for questions before. I think that Vicky wants to move a bit, so please. Okay, so let me start talking a bit about the proofs. And let me recall, I think a good half, solid 3/4 of the audience already know what a blow-up is, but let me recall this very quickly. What is the motto? The motto is that if you have a complex surface, blowing it up will separate the complex tangent directions at that point. So you have a local model. This is defined by one equation in the product of C2 times CP1, where I put coordinates x, y on C2 and st in CP1. And you have a projection down to CP2. And this is a local model. And you can check that over every point in CP2, you see exactly one point in this other new variety, S tilde, except over the origin, where you see the whole CP1. And this CP1 is exactly killed by the projection, it's squeezed down to a point. And if you do a bit of computation and you think about it a bit, this is an embedded CP1, so it's a smooth CP1, it's a smoothly embedded S2 of self-intersection minus 1. In practice, what happens? If you have a surface and you blow it up, the new surface will be diffeomorphic to CP2, to the surface that you have, connected some one copy of CP2 bar. Great, we understand the topology of the surface globally. What happens to curves or to submanifolds inside our surface? If S contains M curves intersecting transversely at one point, say it's contains a line arrangement, and you blow up at that point, what happens is that the curve, the so-called exceptional divisor, this sphere of self-intersection minus 1, depicted in green, in red in the picture, will intersect some curves upstairs transversely, each corresponding to the curves that pass through the point. And you essentially you kill one point, this point of intersection. Then this point of intersection exists no more. And the self-intersections of the component that go through it, assuming that they are distinct, drops by 1 for each of the component. And these are the numbers that appear in light blue. If you have things of self-intersections A, B, and C, when you blow up, the self-intersections become A minus 1, B minus 1, and C minus 1. So there will be two parts now. The first part is about the first two theorems, about the line arrangement that had only points of odd multiplicity, and the part about things that only had even multiplicities. So I call odd a line arrangement if all the multiplicities are odd. So these are the line arrangements that appeared in the first two statements in the proof, in the first two statements. And examples of this are, well, line arrangements with only triple points, which, as you might have guessed, I like a lot. And finite projective planes over finite fields of characteristic 2. The multiplicities of all points are odd. And a small combinatorial observation is that if all multiplicities are odd, then automatically also the degree of the line arrangement is odd. Think about it. So what do we want to prove? We want to prove two statements. While it's not completely clear that the first statement implies the theorem, but the first statement that we want to prove is that a certain linear combination of the number of points of multiplicity m is congruent mod 16 to the degree minus 1. And while the first statement that I've given you about triple points had a mod 8 congruence, this has a mod 16 congruence, so I guess 2/3 of the audience knows where I'm going to prove this statement. And the second inequality, the second statement that we want to prove is that if A is not a pencil, so if it's not the silly line arrangement, then this inequality holds, so the sum of m minus 9 Tm is bounded from above by minus 1 minus 7d. So we've defined blow-ups, we better use them. So what do? We take our line arrangement and we blow up at all singular points. So what happens is that in the blown up manifold, we see a bunch of spheres that are pairwise disjoint because we killed all their pairwise intersections. And each of them has strictly negative self-intersection because since it's not a pencil, every line contains at least 2 points. We started with self-intersection plus 1, and we dropped it down by at least 2. So it's strictly negative. And this collection of spheres...
I'm a bit confused. You're talking about line arrangement, pseudo-line arrangement. I think what category are you in this moment?
So now we're thinking, for the first statement, we're thinking about locally flat, something that is locally flatly realized. And in the second case, something that is smoothly realized.
Okay, but if you blow up, you need a complex direction to separate things.
That is correct. But when you have a transverse intersection that is positive, you can always isotope it to something complex, and then use the local model of the blow-up in the complex setup.
That's true?
Yes.
Okay.
But thank you. That's actually a very good point. The local model, we can always find sort of a complex local model and blow up locally as if things were complex. So that's a very good point, Paolo. Thank you. So now we have a bunch of spheres that have negative self-intersections in some blow-up of CP2. And this blow-up, well, we've done T2 blow-ups for the points of multiplicity 2, T3 for the points of multiplicity 3, and so on. So the total number of blow-ups is the sum of the TMs. So we now take the complement of an open neighborhood of these lines. And I want to make two claims. Well, you had seen it coming. Spin structures will have to enter the picture if we want a mod 16 congruence somewhere. So the complement of the line arrangement, well, of the strict transform of the line arrangement, is a spin-4 manifold, and its boundary is a union of length spaces. It doesn't really matter. Well, it will matter later which spin C structures, which line arrangements they are. And actually, we can find a spin structure on this Z that restricts to a specific spin structure on its boundary components. And more precisely, we want the spin structure that extends to the linear plumbing of +2 spheres. If an I in the first line is odd, this is automatic. So there's a bit of work to be done only when an I is even, and then you have two spin structures, and you have to worry a bit about what is going on. So for point 1, here is where the assumption that the line arrangement is odd comes in. So the strict transform, so the A tilde, the union of these spheres, has total homology class, which is the sum of its components. And we can compute this homology class essentially by intersecting with the exceptional divisors with the -1 spheres. And this is just some linear combination of generators in H2 in the second homology of CP2 blown up a bunch of times. And this class is odd, so it's congruent to the second Stiefel-Whitney class of CP2 blown up, of Y, of CP2 blown up a bunch of times. In other words, you can say that it's a characteristic vector for the intersection form. These are two equivalent things when there's no two torsion in the picture. And so when you remove it, you remove something, remove a neighborhood that supports the second Stiefel-Whitney class. So the Stiefel-Whitney class in the complement vanishes, so you get a spin structure. And the second part is actually a bit of playing with tubing and detubing spheres. You start by tubing the spheres. You realize, oh, I understand exactly what the spin structure on the boundary of this gadget is. And then you detube things and you realize, oh, I can play with the spin structures and obtain the result that I want. So actually, in this proof, it's a bit weird, but I feel like we had to use Hager-Fleur homology. So we had to jump back from 1966 to, I don't know, 2004-ish to prove this thing. But I think it's a huge overkill. It's just that I didn't have the energy to tune the proof and make it a bit simpler. So I think one doesn't need Hager-Fleur homology, but for convenience, we used it just because why not? So now we have equipped our complement of the spheres upstairs with a spin C structure and we understand the restriction of the spin C structure to its boundary. And so we plug in the boundary components with spin objects that extend the given spin structures on the boundary. And so by construction, we get a spin-4 manifold, which is now closed because we capped off all the boundary components. And actually, we can compute both its signature and its Euler characteristic because we understand perfectly well what we have removed and what we glue back. So the signature is the signature of Y. From Y, we removed a number of spheres of negative self-intersection. So the signature goes up by d. And then we plugged in a bunch of things of positive, that are positive definite. So we add the signatures of those. And the signatures of those depend on the total sum of the total self-intersection of A tilde, which you can compute in two different ways. You can either compute it by squaring the homology class, or you can compute it by saying, well, every line has been, the self-intersection has dropped by 1 for every line, every time we did a blow up on that line. So every point of multiplicity m removes 1 from m lines. So every point of multiplicity m drops the self-intersection by 1. Anyway, this is just a cute, simple computation. And we can compute B2, and it's roughly the same computation, and we get these two numbers. What do we do now? As expected, we apply Rochlin's signature theorem to prove a mod 16 congruence. So the signature has to be congruent to 0 mod 16, and if you repackage the congruence, you get exactly the congruence that we wanted, that the sum of m minus 1 tm is congruent to d minus 1 mod 16. And for this, and you can also repackage this in a different way. You can make it as a corollary of the Kerver-Milnor theorem. And so Rochlin's theorem is smooth, but I had promised you something for locally flat objects. Turns out that the proof of the Kerver-Milnor theorem can be adapted to locally flat spheres. So you can tube the things together and get a characteristic sphere and then apply the locally flat version of Kerver-Milnor theorem, and you get the same congruence mod 16. And if you want the inequality, well, you apply the 10/8 theorem that tells you that the signature cannot be too large with respect to B2. Namely, 10 times the signature is bounded from above by 8 times B2. And you get the other inequality with the sum of the m minus 9 TMs. You can play with slightly better versions of Furutas 10/8. There's a 10/8 plus 4 theorem. These give you marginally better results. Or you can use the 11/8 conjecture and have a conjectural statement that is slightly better and changes the coefficients in the sum, but not by very much. It's not a huge improvement in my view. Yes.
So, do you get a potential like counterexample to 11/8 this way?
Yes. Like potentially, yes. I wouldn't know where to look for them. Like you have to have points of relatively high multiplicity. They have to be all odd. I wouldn't know how to even start constructing one of these objects. I wouldn't even know, I don't know of a combinatorial, I don't think I know of a combinatorial line arrangement that would violate this and that we could plug in. So yeah, maybe this is a good point. So odd line arrangements are exceptionally rare.
So just as a follow-up to Laura's question, if you assumed these were real arrangements, do you get something closer to the 11/8? By some other, I mean, can you prove whatever?
So for real line arrangements, you have Melchior's inequality, which is just a lot better than our inequality.
Okay, so it's even stronger than what you would get from 11/8. Okay, great.
So what about the BMY line? There's a conjecture there too.
I wish. I wish that I could find counterexamples. It's one possible strategy, not necessarily with line arrangements, but there are more general things that you can look at, like conic line arrangements or curve arrangements or rational cuspidal curves. And I've thought a bit about that, but coming up with things that would violate the BMY inequality, but are not obviously topologically obstructed and that you can construct, that imposes lots of restrictions. So with LoRa, we had thought a lot about rational Caspilal curves and how to construct them. And we thought, is there any systematic way of constructing things? And we got nowhere. Did you get anywhere? No? Okay.
Just another follow-up to Laura's question. How sharp are your inequalities? Like, can you construct some odd line arrangements that are close to the inequality, to the equality?
I think that everything that we can construct that is symplectic or smooth but not algebraic comes from essentially deforming something pre-existing and maybe adding lines to make things like in what Laura and Olga and Marzi did was essentially to perturb something algebra geometric and then add extra lines to somehow pinpoint one extra point in some way. And definitely if you start from something and you deform it, the inequalities become weaker. So if it's satisfied from the original one, it's satisfied for the new one. So whatever you construct this way will not violate our inequalities, which are weaker than say Hirzebruch's one. So I don't know. We don't have a good way of constructing these objects, I think. And I don't know how to, like, I'm trying, but I don't have a good construction yet. Oh.
Can you unmute it, please?
Hello. Okay. Maybe I missed something. Could we, am I too loud? Could we use similar techniques for higher degree curves instead of lines? Do we care? Do we want to?
I kind of care. With Laura, we cared a lot about conic line arrangements or cubic conic line arrangements. These techniques, so what I told you so far works fairly well, actually very well for rational arrangements of rational curves. So conic lines and cubic conic lines, if the cubics are singular, then you can say something very similar. So in the first paper, at least, I did say something about this case. The problem is that the combinatorial problem is already very complicated for lines.
I know.
And getting up in degree, it just gets a lot wilder, and singularities get weirder. So,
Okay,
but yeah, you can say more.
Thanks.
And what I'm saying next will also work in higher, for higher degree and higher genus. Great. So let's go to the next bit. So let me give a definition. A line arrangement fix some integer q, positive. And we say that a line arrangement is q divisible if q divides all multiplicities at all points and the degree as well. For instance, if q is equal to 2, we say that such a line arrangement is even, and this was the kind of line arrangements that appeared in the third main statements from earlier. So the main theorem that we proved with Paolo is that if A is a q divisible line arrangement, and it's not a pencil, then we have this Hirzebruch type inequality where we bound some linear combination of the TMs. And if you plug in q equal 2, then you get the statement that I had promised you at the beginning with the sum of the m minus 4 TMs. So I want to go a bit into the proof. I kind of have time, yes. And since the left-hand side is decreasing in q, we might as well suppose that q is a prime. We can take the smallest, if q is not a prime, we take the smallest prime that divides q and replace it by that. And we get a stronger inequality. So same old, how do we start things off? We blow up at all singular points. And now, similar to what I was mentioning earlier about the Kerber-Milnor theorem, we get a bunch of spheres in this manifold that I still call Y, which is a blow-up of P2 at the same number of points. And we tube the spheres together to get a single two-sphere that I call B in this big 4 manifold upstairs. And there's a cute algebra topological lemma that tells you that if you are starting with a Q-divisible line arrangement, then there exists a Q-fold cyclic cover of Y, which is branched exactly over this two-sphere. And this is something that I learned from Laura's and Danny's paper, and that I spent a lot of time thinking about ever since. And we can compute the classical invariance of this manifold. We can compute its Euler characteristic by inclusion-exclusion, essentially. We can compute its signature using the G-signature theorem. It's a bit ugly, but okay, it's a computation. And we can compute its B1. This can be viewed as a corollary of work of Gilmer from the 80s, or as a corollary of the Goldschmidt lemma. It's a group theoretic lemma. And let me remark, well, first of all, we suppose that B was a two-sphere, so we know what its Euler characteristic is, and it's 2. And we know its self-intersection, because we essentially had computed it earlier. This is the same as the self-intersection, the sum of the self-intersections of the spheres in the pre-image of the line arrangement. And let me remark that the G-signature theorem, well, the original version was maybe for smooth group actions, but actually in dimension 4, since locally flat things are globally flat, the proof goes through in the locally flat category. So whatever computation we do here also works for locally flat objects. And well, we have chi and we have B1, so we can compute B2. We have B2 and the signature, so we can compute B2 plus and B2 minus. And let me not do the computation, but it's not complicated. And the key point is that, and this is somehow a trick that I learned from Laura's and Danny's paper, inside X, we see a bunch of a bunch of curves that have negative self-intersections, and they're pairwise disjoint. And indeed, we see the sum of Tm such lines. I will show you in a second. Each of them actually has self-intersection minus Q. And now you apply the inequality that if you see a certain number of pairwise disjoint negative spheres, this gives you a lower bound on B2 minus. You apply this inequality, you do some computation, you redo it because the first time you will do a mistake, and then you get the theorem that I had stated earlier. So how do you get these spheres? Actually, this is very easy. At every point you blow up, you see a -1 sphere appearing. And when you take the p-fold cover, this sphere is Q2-1 covered by some surface of some genus. And the self-intersection of this surface, since there's no ramification along it, the self-intersection will multiply by Q. So we started with something of self-intersection -1, and it becomes a self-intersection minus Q. And you can actually compute the genus. Not that it's relevant, but I just put it out for completeness. The genus is Q minus 1, M minus 2 divided by 2. And so this concludes the proof of the second statement. Let me say something about configurations. I like configurations, and I like something more. So recall that an NK configuration is a configuration of an arrangement of n lines that contains n points, such that each line contains k of these points, and each of these points lies on k of the lines. And we want to give a bound on n in terms of k. And to do that, we want to use even arrangements. So out of an nk configuration, we want to produce an even line arrangement. And if n and k are both even, we essentially have already something even. We have an even number of lines. All multiplicities at the n points are even. And if there are other multiplicities, we can always perturb them away and get a bunch of double points. And the double points have even multiplicity. So we get something even. So if n is odd, well, we just say, well, chuck away one of the lines, and this fixes the parity of the degree. And if k is odd, we can always take a k-fold point and perturb it into a k minus 1-fold point and a bunch of double points. And then we apply the inequality about even line arrangements that was stated a while back. And we get that if an nk configuration is topologically realized, then n is at least k squared minus 5. So where do we sit among the things that we knew already? So if we look at complex configurations, Hillesbrook's inequality tells you that n has to be at least k squared plus k minus 5. So, with respect to Hillesbrook, we're not faring so well, but we're also in a much softer category. So, Combinatorially, on the other hand, it's easy to prove, and if you get bored in the last 5 minutes of the talk, you can prove it, that n has to be at least k squared minus k minus 1. So actually, the gap between the two is not so large. And what we prove somewhere sits more or less halfway through these two bounds. And let me mention that with a slight variation of the proof, and this is something that I've done in collaboration with a few people who are in the room, Dominik Desch, with Laci Koltai, Mateusz Kujawski, and Mark Penkovic. If n and k are even, this is not written in the slide, but if they are even, then we can actually bump it up slightly to k squared minus 2 instead of k squared minus 5. And let me mention that smoothly, Paolo Aceto and Duncan McCoy and Jung Park actually proved that if something is smoothly realized, so slightly more rigid category, an nk configuration requires n to be at least k squared minus 1. So there's not a huge gap between these categories, and I think it would be very interesting to find anything that is in between these various categories. We know that the locally flat category is very different than the smooth category in dimension 4. We know that smooth is very different than complex, but somehow finding counterexamples in this area, I don't know, I find it very hard and I don't really know where to go. And even finding something that is between smooth and symplectic, I think anything in this neighborhood of results would be very interesting. Are there questions? When did I oh, there's a question from Marzi.
So, is there anything so there's missing an obvious column for symplectic, or is it the same as complex, or am I missing something?
I don't know of any symplectic obstruction that is not smooth, I think. So for symplectic, you get the same as smooth. Thanks.
And is there a locally flat example attaining the bound k squared minus 2?
No clue.
No?
I don't know. I don't have an example. I wish.
So it could be the same as the smooth bound?
It could be, yeah. Yeah, it could well be. But just maybe we're not smart enough to prove something strong. Okay. When did I start, Vicky? Yeah, I know that the clock says 54, but when did I start? Yeah, let me say something about, still in CP2. So as I mentioned earlier, projective planes over finite fields are somewhat extremal configurations in the sense that they're given k, they minimize n combinatorially. And since in our category, in the locally flat category, for k not too small, k squared minus 5 is larger than k squared minus k plus 1, extremal configurations generically are not realized in the locally flat setup. But I kind of want to spend a bit of time thinking about finite projective planes. So an extremal configuration in this sense is called a finite projective plane. And projective planes over finite fields are one example of such configuration, but there's more. And an equivalent description of such an extremal configuration is a configuration that satisfies the axioms of a projective plane. For every 2 points, there's a line, and every 2 lines meet at a point. So, as I said, the main examples are projective planes over finite fields, but there's more. There are planes that do not satisfy the Desargues theorem that every finite projective plane satisfies. For instance, the whole plane for k equal to 10, I believe. And a corollary, well, almost a corollary of what we do is that no finite projective plane is topologically realized. This is slightly different than what Laura and Danny did in their paper, because they restricted to projective planes over finite fields, or to configurations that contain such finite projective planes. And one proof is, well, the proof using configurations, so perturbing to get an even line arrangement. But actually, a proof that I like maybe slightly better is to say, if you have a projective line arrangement, and if you remove a point and all the lines through that point, you get an affine line arrangement. And an affine line arrangement is divisible. Like if you look at the finite projective plane over affine plane over FP, it has p squared points, and through every point you have p minus 1, p lines, because you removed like a pencil of lines. And so you can use the other result about Q-divisible line arrangements to get to the proof. And I want to mention just a bit of extra work, which is a cute lemma that is entirely combinatorial. If you have a line arrangement that is not a pencil, then it has to have at least as many critical points as it has as its degree, which is something that to me was not at all obvious. The proof is very mysterious. I don't understand. I mean, I understand it. It's one line, and I understand the steps, but it's a proof by contradiction, and I don't understand where it comes from. So I'm just a bit baffled by it. Anyway, I think I will stop here. Sorry.
Thank you, Marco. Questions? No further questions? Then we can continue the discussion in the coffee break, which is not right now. I will let you know in a minute. But let's thank Marco again. So welcome back, everybody, and first of all, thank you for your cooperation in the break. It is my pleasure to introduce the last lecturer for today, Andrew Lobb from Durham University, and he's going to tell us about inscription problems and symplectic geometry. Enjoy.
Well, thanks very much for the invitation. It's a pleasure, as always, to be back in Budapest. I'm going to start with the definition of a Jordan curve. A notation for a Jordan curve is always going to be gamma. And gamma is just going to be a subset of the plane that's homomorphic to the circle. Alternatively, you can think of it as the image of an injective continuous map of the circle into the plane. That's what a Jordan curve is. And here's a conjecture due to Toeplitz from around 1912. Known as the Toeplitz conjecture, or the square peg problem, or Toeplitz's square peg conjecture. And it says that given any Jordan curve gamma, you can always find 4 points on the Jordan curve at the vertices of a square. We say that gamma inscribes a square. And something about that terminology might imply to you that the edges of the square lie entirely inside the region bounded by the Jordan curve. That's not the case. We're just going to be looking for 4 points on the Jordan curve at the vertices of a square. So this conjecture, as stated, is appealing from a number of points of view. It's very old, it's unsolved, and it's sort of easy to write down. We'll get on to motivation for making the conjecture in a second, But before I do, I wanted to point you to this survey article of pre-symplectic approaches to the square peg problem and its relatives by Matchka, which appeared in the AMS notices and is very readable. All right, so why make this, this conjecture at all? So first of all, suppose you ask the related question, but for inscriptions of triangles. Suppose you've got your favorite triangle, maybe an equilateral triangle, maybe the 3, 4, 5 triangle. Well, you can always find an inscription of that triangle in any Jordan curve, so no hints about how to prove that. But that means that the inscribed triangle problem is easy. It doesn't matter which triangle you pick. On the other hand, if you've got a pair of dissimilar ellipses in the plane, so ellipses of different eccentricities, different ratios of the major axis to the minor axis, no matter the size of the ellipses or how you arrange them in the plane, they're never going to overlap at more than 4 points. And so that, if you think about it, means that dissimilar ellipses can never inscribe similar pentagons. So, for example, the circle inscribes a regular pentagon, so no non-circular ellipse ever inscribes a regular pentagon. So sort of pentagonal peg problems have negative answers, even just for ellipses. And of course, quadrilaterals represent the middle ground, so you can ask quadrilateral peg problems, and the square is the first quadrilateral that you think of, and so that's why Terplitz posed it for squares. Let's think about quadrilaterals. Here's a hierarchy of quadrilaterals sort of suitable to this problem. In the top left is a square, and we're thinking of quadrilaterals as really just the collection of its vertices. And up to similarity, of course, there's exactly one square. Brilliant. And then in the top right, that's a rectangle. There's a one-parameter family of similarity classes of rectangles, if you like. They're classified by their aspect angle. That's the angle that the diagonals of the rectangle make with each other. In the bottom right, that's a cyclic quadrilateral. So a cyclic quadrilateral, as the name suggests, is just a quadrilateral, all of whose vertices lie on a common circle. And there's a 3-parameter family of those. In the bottom left is a cyclic trapezoid, otherwise known as an isosceles trapezoid. There's a 2-parameter family of them. And these are just the trapezoids that you get by intersecting a circle with 2 parallel lines. So these similarity classes of quadrilateral nest inside one another. And I've arranged them in a table. This is the problem table, distinct from the table problem. And on the left, I've got this column of quadrilaterals. So at the bottom is the square. There's a unique similarity class of square. So that's 0-dimensional. Rectangles, isosceles trapezoids, cyclic quadrilaterals, and then general quadrilaterals, of which there is a sort of 4-parameter family. And along the top, I've got regularity conditions on the Jordan curve. So that isn't quite a hierarchy, because smooth Jordan curves and piecewise linear Jordan curves are disjoint sets. There we are. I've listed smooth Jordan curves, piecewise linear Jordan curves. Turns out rectifiable Jordan curves are interesting. Rectifiable Jordan curve is just a Jordan curve that isn't necessarily smooth, not necessarily piecewise linear, but is finite length. And then continuous Jordan curve just means a Jordan curve with no regularity conditions. So you can ask peg-like questions for any box on this table. Now I'm going to fill in some x's in the top row, and what that means is that it's not true that you can inscribe, for example, if I look at the top left-hand box, it's not true that you can inscribe every quadrilateral in every smooth Jordan curve. And of course that can't be true, because the only quadrilaterals that inscribe in a circle are the cyclic quadrilaterals. All right. So there are all these peggy questions, and the Terplitz square peg problem is the bottom right-hand box. Is that okay? All right. I'm going to fill in a check mark in the bottom left. And the check mark indicates that squares inscribe in every smooth Jordan curve. And this is a result due to Schnirelmann in 1929. That's a Bordism argument. And Bordism argument runs roughly like this. If you got your favorite smooth Jordan curve, well, you start with a non-circular ellipse that inscribes a unique square. And then you deform that ellipse until it's your favorite Jordan curve. The count of inscribed squares changes as you do that, but it always changes by plus or minus 2. And so since you started with 1, you end up with an odd number of inscriptions generically. And the thing about odd numbers is they're never 0. And so that's why there's a square in every smooth Jordan curve. Turns out that implies there's also an inscribed square in every piecewise linear Jordan curve. More about that result in a little while. There's also a box to fill in there. So in about 1977, Vaughan proved something. He never wrote it up himself. As far as I know, the first person to write it up was Meyerson in 1981. He showed that every Jordan curve, that's with no regularity conditions at all, inscribes at least one rectangle. So not necessarily a square, not necessarily all rectangles, but at least one rectangle. And that's a very beautiful argument, and you can find lots of videos about that on YouTube, if you like. Our symplectic story is going to start with that box. So this is the result I proved with my collaborator Josh Green in 2020. What that check means is that every cyclic quadrilateral inscribes in every smooth Jordan curve. So we can fill in some x's here. So in particular, it's not true that every cyclic quadrilateral inscribes even every piecewise linear Jordan curve. If you give me a cyclic quadrilateral that isn't a trapezoid, and I can find a triangular Jordan curve, and triangular Jordan curves aren't smooth, of course, because they've got 3 vertices. You can find a triangular Jordan curve that doesn't inscribe that non-trapezoidal cyclic quadrilateral. And, of course, we can fill in the checkboxes there because of this hierarchy. So this result is optimal from a couple of different directions. Of course, if you're looking for the largest class of quadrilaterals that inscribe in all smooth Jordan curves, you're never going to get any larger than the cyclic quadrilaterals because the circle is itself a smooth Jordan curve, so the only ones you're allowed to consider are the cyclic quadrilaterals. And then if you weaken smoothness down to piecewise linearity, it stops being true. All right, so I'm going to tell you how to prove this result. Check GL 2020. Here we go. So first of all, pick your favorite similarity class of quadrilateral, which we'll call Q, and pick an ordering on the vertices. So that's your, I checked with you earlier, and that's your favorite similarity class of quadrilateral, those 4 vertices. And you pick some order on them. And we're going to use that quadrilateral and the ordering of the vertices to give a map from C2 to C2. And that's what we're going to do. And how it works is this. So given 2 points in C, that's the same as giving a point in C2. So given 2 points ZW in C, what you're going to do is complete them to your favorite cyclic quadrilateral. So you're going to add in the points Z prime and W primed. There they are in blue. So that ZW, Z prime, W primed is your favorite quadrilateral, not necessarily cyclic. Said that. Fantastic, and that's the map. The map is just the 2 points you have to add in to form your favorite quadrilateral. So ZW goes to Z prime, W prime. Does that make sense? Take that as a yes. And there you go, that's the map. Turns out that's a complex linear map from C2 to C2. Brilliant. So now suppose we have a Jordan curve in the picture as well. And suppose we have both that ZW lies in gamma times gamma, and the image of ZW under this map lies in gamma times gamma. Well, what's that saying? That's just saying that ZW, Z prime, and W prime all lie on gamma. So, if we've got the point P on gamma times gamma, and the image of P under this map on gamma times gamma, then we've won the game. We've found an inscription of this quadrilateral inside gamma. Does that make sense? All right, so let's draw this picture in C2, or as near as we can. So in this picture, I've got this vertical cylinder here, and that vertical cylinder is meant to represent gamma times gamma, the torus, so you can imagine joining the top to the bottom if you like. And then the slanted cylinder, this is not a useful device. Yeah, well, you can see there's a slanted cylinder. And that slanted cylinder is just the what you get when you apply this map phi q to gamma times gamma. So that's another torus living inside C2. And the point P, marked in red, is the point ZW, and that gets taken to point P prime, Z prime, W prime. And the thing about the point P prime is, well, certainly it's in phi q of gamma times gamma, because you just applied phi q to the point P, and P was in gamma times gamma. But also, because this is an inscribed quadrilateral, it lies in gamma times gamma as well. So it's an intersection point between the two tori, gamma times gamma and phi q gamma times gamma. Now there's a circle's worth of intersection points as well. And what's going on there? So these are the points that look like ZZ, where Z lies inside gamma. Because let's think about this linear map phi q. Suppose you feed it a repeated point ZZ. How are you going to complete that to a cyclic quadrilateral, your favorite one, Q? Well, the only sensible way to do that is if you think about the infinitely small cyclic quadrilateral. So ZZ should spit out ZZ. So you just complete it to a cyclic quadrilateral where all four vertices coincide. And such cyclic quadrilaterals, of course, they're inscribed in gamma. There's one infinitely small cyclic quadrilateral each point of gamma, but we're not really interested in finding those. So we're interested in intersection points that look like this P prime, but not intersection points that look like this loop of intersection down here. So there we are. So that says in a sentence what I've just been attempting to say. Problem of finding inscriptions of Q in your Jordan curve gamma can be formulated as finding intersection points between two tori inside C2. So in the case of rectangles, there's a quotient of this set up by a Z mod 2 symmetry, and Hugelmeier used it to show something that isn't quite how I've written it on this slide. Hugelmeier showed that for every Jordan curve, a third of all rectangles inscribe in it. It might not be necessarily the same third of all rectangles for each smooth Jordan curve. And by a third, I mean a third of the possible aspect angles of the rectangles. So Hugelmeier gave an argument for that using just smooth topology. Symplectic topology, however, also enters the picture. When gamma is smooth and Q is a cyclic quadrilateral, the situation has a framing in terms of symplectic geometry, and framing there is used entirely in its colloquial sense. Turns out there's a symplectic form on C2, called symplectomorphic to standard form, that makes both of these tori, gamma times gamma, and its image under phi q, Lagrangian. So now you've reduced finding inscriptions of your given cyclic quadrilateral in your smooth Jordan curve to a question of finding intersection points between two Lagrangians in C2. And, well, what is a Lagrangian? So a Lagrangian inside C2, let's say, is, what does it mean to be Lagrangian? Being Lagrangian is a condition on the tangent planes. So tangent plane to a Lagrangian is always a plane on which the symplectic form vanishes. That's exactly what it means to be Lagrangian. And so you think about this situation. Suppose you've got an immersed Lagrangian torus. If you have a circle on that torus, you think about the path of tangent planes as you travel around that circle on your torus. After a few choices, that gives you a map from the fundamental group of the torus to the fundamental group of the space of Lagrangian two planes in C2. And it turns out that the fundamental group of that latter space is the integers. So this, once you've got an immersed Lagrangian torus, out of that you get a non-negative integer. And you construct that by looking at the image of this homomorphism, which is a subgroup of the integers. And so it looks like n times z, where n is some non-negative integer. And Polterovich and Viterbo showed independently in about 1991 that if T are an embedded Lagrangian torus, then you have to have nt equals 2. So there's a fact about immersed versus embedded Lagrangian tori. What's that got to do with us? We're looking at intersections of two tori. So here are our two tori. The points of intersection we're interested in are the, oh my God, are the blue dots. And the points of intersection that we're not interested in are that loop of intersections in the middle. Now, it turns out that that loop of intersections is a clean intersection between the two Lagrangians. And so that means you can do a surgery to surgery it away. And so this is the situation that you get. So you've got one Lagrangian torus here, another Lagrangian torus there. They meet in this loop that you don't care about. You can smooth that loop away, and the result will be one sort of extra long Lagrangian torus. And now it doesn't have that loop of intersection anymore, but it might have other points of self-intersection, and those other points of self-intersection of that long Lagrangian torus correspond to these blue points of intersection between your original pair of tori. Well, if you compute this number nt for this long Lagrangian torus, you find it's not equal to 2. It's equal to 4, so this long Lagrangian torus can't be embedded, so there must be these points of self-intersection. So these two tori must have intersected, so you must have had inscriptions of your cyclic quadrilateral. So that's how that result is proven. There we are. So we're back to the problem table. Let's fill in a little bit more. So the boxes with these implication arrows. Yeah, so it turns out that if you know that you can inscribe every rectangle in every smooth Jordan curve, you can conclude that you can inscribe every rectangle in every piecewise linear Jordan curve. And I'll explain the reason for that in a second. As we mentioned, it's not true that every cyclic quadrilateral inscribes in every piecewise linear curve. As far as I'm aware, it's not known that every isosceles trapezoid can inscribe in every piecewise linear curve. So that's a rather intriguing open question. But let's think about these implication arrows a little bit. So, all right, yeah. Let's see. So let's go back to Schnirelmann. So in 1929, Schnirelmann showed that every smooth Jordan curve inscribes a square. And he probably emailed this result around his friends, and publicity department of his university probably put it on his website, and might have been a Quanta article or two. Anyway, so if you're alive at the time, you probably would have heard about this result, and you might have thought maybe Schneermann solved the whole thing, because what you could do is, given an arbitrary Jordan curve, continuous Jordan curve, why can't you just approximate it by a sequence of smooth Jordan curves that gets closer and closer? Each one of them inscribes a square, and so by compactness, surely there should be a subsequence of squares that limits to an inscribed square on the limit Jordan curve. And the problem with that argument is it's hard to get around the possibility that that subsequence of inscribed squares might be getting smaller and smaller, so limiting to a degenerate inscribed square on the limit Jordan curve. And that's the problem that we call shrink out. And so one thing you want to try and do to extend results from smooth curves to other classes of Jordan curve with lower regularity is to obstruct shrink out. That's what happens, for example, if you think about rectangles inscribed in smooth Jordan curves, whether you can extend that result to piecewise linear. Well, if you take a piecewise linear Jordan curve and you smooth it in a sensible way, adding little almost circular arcs at the vertices, and then you make those smoothings sharper and sharper, you'll see that you never get any inscribed rectangles that shrink out towards the vertices. So shrinking out doesn't happen in that approximation. That's why you can conclude that piecewise linear Jordan curves inscribe all rectangles. It's impossible to see that for cyclic Jordan curves in the same way, because for cyclic quadrilaterals in the same way, because not every cyclic quadrilateral inscribes even every triangle. So if you take smooth approximations to these triangles, you can find inscriptions of cyclic quadrilaterals, but some of them at least must be shrinking out towards the corners as you make the approximations better and better. All right. So there that is. So we want to get around shrink out. So how are we going to do that? So this thing called Jordan-Fleur homology. So here's a little smaller version of that picture. So we're interested in the blue intersection points between these two tori, gamma times gamma and the image of gamma times gamma under this linear map. And so you want to prove that a set of blue points is non-empty. And so you might think that the way to do that is to just find an element of that set. But I mean, this isn't kindergarten. That's not how we're going to do things. Now what we're going to do is we're going to take that set of blue points and make them generate a vector space. And then you might think what you do is try and show that vector space is non-zero, and then you'll be done. But, you know, it is an amateur hour. So what you do is you find a differential on that vector space, and then you take homology, and then you check that that homology is non-zero, and then that's how you prove that that set of points is non-empty. So that's kind of a bit of secret math that I'm sharing with you because it's so late in the day. But that's how you should prove that a set is non-empty. Construct a chain complex, take the homology, and prove that the homology is non-zero. So that's something that Josh and I did for rectangles in 2024, and Adam Barber did for isosceles trapezoids earlier this year. And, well, it's a Lagrangian-Fleur chain complex. JFC doesn't stand for what you think it stands for. It stands for Jordan-Fleur chain complex. And it's generated by the non-degenerate inscriptions of these rectangles or isosceles trapezoids in gamma. And it's a Lagrangian-Fleur complex, and so the difficulty in defining it is making sure that you can come up with a sensible differential that avoids this degenerate circle of intersection points. All right, but we do that, and we call its homology Jordan-Fleur homology. And it turns out that that homology is two-dimensional, so that gives another proof that rectangles and more generally isosceles trapezoids inscribe in every smooth Jordan curve. Brilliant. What else can we do with it? Well, There's a grading on it, so there's a homological grading on this thing, otherwise known as a Maslov grading. And it's supported in gradings 2 and 1. It's one-dimensional in each of those gradings. There's also a real filtration on this homology. So each generator of the chain complex G, remember that's just an intersection point of these Lagrangian tori. In other words, it's just an inscription of your isosceles trapezoid into your Jordan curve. Each generator comes with an associated real number called the action. And a differential of the chain complex drops the action. It drops it by an amount that's the area of a pseudo-holomorphic disk that appears in the definition of this differential. All right, so you've got a sort of real grading that's lowered by the differential. That's nothing more than a filtration. So you get a filtration on the homology, a real filtration, and so that gives you two real numbers. The associated grading for each generator, the generator in degree 2 and the generator in degree 1. And we call those L2 and L1. I'm going to try and use these things to obstruct shrink out. All right, so in the setting of Lagrangian flow homology, these go by the name of spectral invariants. They're not independent of each other, at least in the case of rectangles. So I'll just continue to write one of them for now, L2. On everything I say applies equally to L1. Brilliant. So the usefulness of them is to do with a couple of things. So first of all, there's always a generator that realizes the spectral invariant. So there's always an inscription of the isosceles trapezoid or of the rectangle whose action agrees with the spectral invariant. And so knowing that, if it turns out that a large action means a large inscription, then that's the thing that could possibly be useful in obstructing shrink-out, broadly speaking. So let's see if that is actually true. Does a large action mean a large inscription? So here's an inscription G of a rectangle in a Jordan curve gamma. And this corresponds to an intersection point between the two Lagrangians. It corresponds to a generator of the Jordan flow chain complex. So it comes with an associated action. That's a real number. What is that real number? Well, we call it the double ice cream number. And it's the area of this shape, the positive area. So it's like two ice cream cones meeting at their tips. And, well, clearly this has got something to do with the size of the inscription. If the action were just the wafer part of the ice creams, then it would be nothing more than half the area of that inscribed rectangle. Now, it's not quite that. There's sort of the error term given by the ice cream bit of it, and that sort of depends on the Jordan curve. But nevertheless, this clearly has something to do with the size of the inscribed rectangle. So this is what one can use in good cases to try and obstruct shrink out. So I'll give you a list of some of those cases in a second. The second part of the idea of how to use it, though, is the following. The spectral invariant turns out to depend continuously on its inputs. So in particular, for example, you can deform the Jordan curve and you get a continuous continuous set of spectral invariants. So you can think about starting with a Jordan curve which you completely understand the spectral invariants, such as the case of a circle, and then maybe deforming it, perhaps in a clever way, to your Jordan curve of interest. It also depends continuously on the isosceles trapezoid. In particular, it depends continuously on the aspect angle. That's the angle that the diagonals of the isosceles trapezoid or of the rectangle make with each other. And you can make sense of the limits as theta goes to 0 and theta goes to pi, and try to use that in some way to tell you more about the action. So here's a question. Is there a microphone?
For what topology is it continuous in the curve? I mean, what do you have in mind at the moment, anyway?
In mind, I've got a... I have to think about that to give you a precise answer, I think. Yeah. Well, I think basically any topology that you pick, actually. Well, okay. Yeah, I think that, yeah, anyway, let me think about it, give you a more precise answer. All right. So here are some theorems proved using the action to obstruct shrink out. So this involves rectifiable curves. So this is a result that Josh and I proved in 2024. We showed that there's a connected interval of length, the Bieberback number. Bieberback number measures how close your Jordan curve is to being a circle. So it's a number between 0 and pi exactly when gamma is a circle. And when gamma is rectifiable, there's a connected interval of length, the Bieberback number. We named this number after our favorite musicians, by the way. Such that whenever theta lies inside that interval, then gamma inscribes a rectangle of that aspect angle. A little while later, Asano Ike proved that you could drop that hypothesis on the Bieberback number and just showed that every rectifiable Jordan curve inscribes every similarity class of rectangle. Their proof isn't Lagrangian Floer theoretic. It involves microlocal sheaves. Still involves spectral invariance. We think their spectral invariants are the same as ours. So we haven't quite figured out what the special ingredient is that means they're able to conclude more than we do. Isosceles trapezoids. So there's a two-parameter family of isosceles trapezoids. Again, there's the aspect angle, which is the angle that the diagonals make. Another parameter that measures how close the isosceles trapezoid is to being a rectangle. This is something that Adam Barber proved for locally Lipschitz graphical Jordan curves. He also has results about rectifiable Jordan curves, although they're a little bit harder to state. And I should note, in the context of microlocal sheaves, that the Lagrangian tori in the isosceles trapezoidal case, as opposed to the rectangular case, are not monotone, and that, I think, means that much of the technology of microlocal sheaves is at least going to be more difficult to apply in this case. Moving beyond rectifiable, we have a result for continuous Jordan curves. There's a subset of measure, the Bieberback number, such that if your angle theta lies in that subset, then you inscribe a rectangle of that aspect angle. So that improves on Vaughan's result that every Jordan curve inscribes exactly one rectangle. Now we get a set of positive measure. So that's where we are. So back to the table. I'm just going to fill in the rest of it now, and then we'll talk about maybe some of them. So there we are. I've given Hugo Meyer a piece of the smooth rectangular peg result. He's owed about a third of that. And AI 2025, that's Asano Ike, not artificial intelligence. And I might have given Josh and me part of that as well if there were room in this table. The tildes imply not full results, but sort of partial results. And I think there's some partial result for isosceles trapezoids and continuous curves that one could get if we combine Adam Barber's work with the work of Josh and me. Broadly open questions, though, of course, remain the original conjecture, which is the bottom right box, Does every Jordan curve inscribe a square? And interestingly, the other box marked with a question mark, does every isosceles trapezoid inscribe in every piecewise linear Jordan curves? I half suspect there's going to be a counterexample out there somewhere, so maybe by the end of the week, somebody can come up with one. I'm going to close. I have 3 final slides talking about a slightly different problem. So there's more ways than this to generalize the Toeplitz square peg conjecture. I'm going to tell you about one of them that's also related to symplectic topology. And it goes like this. So we're going to fix a Jordan curve, and we're also going to fix a quadrilateral. But now, not a similarity class, just literally 4 points inside C. So then you can phrase the question of whether that quadrilateral Q inscribes in the Jordan curve, as is written here. The question is, does there exist a non-constant linear map, Z goes to AZ plus B, that throws that set of 4 points onto the Jordan curve? So why is that? Well, multiplying by a non-zero number A rotates those points by the argument of A and scales them by the magnitude of A, and then B translates those points. So linear maps are just similarities of the plane. So you might be able to guess where I'm going with this given the title of the slide. This is linear inscriptions, and this is a classical inscription problem we've been talking about. You could ask, given a finite subset, which for want of a better letter I'm still calling Q, whether there's a non-constant polynomial that throws Q onto your Jordan curve gamma. And of course, if you allow the degree of that polynomial to be as large as you like, then that's very easy to arrange. So if you do a bit of back-of-the-envelope working out, turns out that the dimensionally correct question to ask is, given a subset of 2D plus 2 points, is there a degree D polynomial, a non-constant one, I should say, that throws those points onto your Jordan curve? All right. So perhaps surprisingly, this also admits symplectic formulations. These are in terms of intersections of Lagrangian tori inside Cn, where n equals d plus 1. And we also have some results here. Cyclic hexagons admit quadratic inscriptions into all smooth Jordan curves. In even higher dimensions, suppose you've got a cyclic 2D plus 2 gon, not a general one, but one that is invariant under rotation by 2 pi over d plus 1. Then that admits a degree D inscription into all smooth Jordan curves. Intriguingly, so I began, when we were talking about symplectic things, talking about the cyclic quadrilateral problem, that you can inscribe every cyclic quadrilateral in every smooth Jordan curve. And I mentioned that this was kind of an obviously optimal result, because if you've got a quadrilateral that inscribes in every smooth Jordan curve, then it had better be a cyclic quadrilateral because it has to inscribe in the circle. Optimality is not as easy in this situation. In fact, it's not even true in an obvious sense. So for example, suppose you just take 8 points that are sort of like the square root of a cyclic quadrilateral. So when you square those 8 points, they land on a cyclic quadrilateral. Then that's an octagon that quadratically inscribes in every smooth Jordan curve, just because its square linearly inscribes in every smooth Jordan curve. So here's a conjecture. The only hexagons which quadratically inscribe in every smooth Jordan curve are the cyclic ones, or their hexagonal subsets of these octagons. And you can make broader conjectures along these lines for other 2D plus 2 gons. But showing, so one direction is, well, establishing this conjecture, I think, probably involves some non-symplectic ideas. So this is something which you might be able to make progress on, even if you don't care about symplectic topology. So I thought it might be a good thing to close this talk with, and so that's where I'd like to end.
Thank you. Any questions?
What about the higher dimensional analogues? So instead of curves, you consider surfaces, and you want to inscribe cubes. Is that considered? Was that considered?
Yes, so that's definitely a good question. So the question is, suppose you've got a compact surface in R3, which vertex sets inscribe in such a surface. So that's a good question, and there are partial results for it. Interestingly, I think the dimensionally correct question to ask about the number of vertices that this inscribing thing should have, I think it's like 7 vertices. So there's no regular shape that would make sense dimensionally. All right, having said that, I don't see a way to approach that question symplectically. What's making these types of questions work symplectically is the fact that smooth Jordan curves are already Lagrangian submanifolds of the complex plane. So it's a good and interesting question, but I don't have a good technique to tackle it.
Further questions? Go on, Mark.
So for the continuous part, you said that there is a measure of subset, this Bieber-Bach number, but is this number not like either 0 or infinite for non-rectifiable curves? Or am I missing something?
Is the number what, sorry?
I mean, either 0 or infinite for non-rectifiable curves, no?
I'm not hearing that.
Maybe question. I missed the definition, sorry.
Yeah, the Bieber, maybe I should go back to
and or what measure are you using on the interval?
Just the standard measure, I think.
Mm-hmm.
Yeah, the Bieber-Bach number is this. So I didn't define what the radius of the Jordan curve is. So the radius is just half the diameter. So the Bieber-Bach number is a number between 0 and pi. That's pi exactly when the Jordan curve is a circle.
Yeah. Okay. Thank you.
I have a question about the details of this Jordan floor homology. So when you define this chain complex, you look at the intersection of two Lagrangians, and when you want to define the differential, you want to look at pseudo-holomorphic curves, right? And how do you avoid that intersection circle? Are you considering only pseudo-holomorphic curves which don't intersect the diagonal?
Yes.
Did you consider the case that you keep track of the intersection with the diagonal and see you would get some more refined invariant that way?
So let me expand on my earlier answer to your question. So there's the diagonal inside C2, which is just point ZZ, where Z lies in C. So what we do is we avoid that divisor. We look at all differentials that avoid that divisor. It's not obvious that's a sensible thing to do, because of course that divisor intersects both Lagrangians non-trivially. So it's not clear that in a positive dimensional family of holomorphic strips, that these holomorphic strips can't wander up to and pass through that divisor. So there's some careful analysis to do to make that definition. As for a more refined version, We didn't consider that. I mean, or we did, but we didn't see how to get anything stronger out of it. Yeah, considering the extra differentials that go between the non-degenerate inscriptions and the degenerate inscriptions, we didn't see what that was going to give us.
Right.
Are there other questions? If not, then let's thank Andrew again. And I thank you for today. We resume tomorrow at 9 o'clock. Don't forget that tomorrow is the free afternoon, so you can make up your mind, do some activities. If you decided to join us with some organized activities, please don't forget to sign yourself. And there are these WhatsApp groups which you can reach via these QR codes Marco made. So join the groups and you will get all the needed information. Thank you and see you tomorrow at 9 o'clock.